Welcome everyone. I am India Jayaratne, an undergraduate student at the Department of Chemistry, University of Colombo. Today I am going to conduct an interview with prominent scientist in the world, Professor Judith Klinman. Professor Judith is a chemist at the UC Berkeley in the field of biochemistry and molecular biology. Good afternoon, Professor Judith.
Good afternoon. Good evening for me and good morning for you. Yes.
Thank you for agreeing to be interviewed.
You're very welcome.
First of all, could you please tell me some details about your childhood and early education, as we would love to get to know them?
Sure. So I grew up in a city called Philadelphia. It's on the East Coast of the United States, and it's a big city. And we lived in the suburbs, which means not in the center, but further out. I went to a public school, which is the school is free. And actually, I grew up across the street from my elementary school. So it was very easy to walk across the street and go to school and come back. And then I went to junior high school in a larger area, further away from my house, and finally a high school. And I really never had a desire to be a scientist, actually, at that point. I was very interested in ballet. I wanted to be a ballet dancer, and anyway, I didn't become a ballet dancer, but I did study ballet and ended up in science. But so I come from a family of four. I was raised by my stepfather, not my father, my mother, and I have a sister. She's actually my stepsister. So we were a family of four, and we were middle class. So our life was pretty easy in that way. I didn't grow up in a wealthy family, but we didn't worry about money too much anyway, a little bit, not too much. And we would go to the seashore during the summer, and, it was a pretty typical childhood for the 1950s in the United States. So I was not encouraged to be a scientist, by the way. That was, my parents didn't come from that kind of, well, my father was in business, my mother was an artist, and, so we can talk about that later, further down in your questions. Yeah.
Okay, my next question is, what is the turning point of your life to become a scientist, and how science became your passion?
Yeah, so that's what I'm saying just a little bit ago, that I really wanted to be, a dancer. It was like, but I had but I was so I went to a very large school. I think there were 1,000 people in my graduating class, huge. But they we were considered gifted, whatever that meant. And they put us in a class with about 30 people, and we just went through all of our high school together. So we had good teachers, and it was a team of two men who taught us physics and chemistry. And I loved it. I just fell in love with chemistry in particular. It just made sense, and it was so logical, and it was fun, and there were beautiful colors. I don't know, I just fell in love. So it was in my junior year in high school, I think, that I decided to become a scientist. Bingo, everything got turned on its side. Yeah.
Okay, that's a very nice story. Okay. Exploring nature of the enzyme catalyst is the main aspect of your research. Can you tell about the improvement of this category of research investigations from your early stages to now?
Okay, so you've heard of Linus Pauling, yeah? The hydrogen bond. He was the one who spoke about the nature of the hydrogen bond. And he had a hypothesis about how enzymes worked. So you've learned about transition state theory, right? You go from a ground state to a transition state. And a molecule reacts, it goes through a transition state. So what Pauling proposed was that the way enzymes work, so this is a large protein is an enzyme. It has an active site. And what he proposed was that the structure in the active site, which is where the chemistry takes place, looked like the transition state, not like the ground state. That was called transition state binding. I mean, it was really just an interesting idea. But when I started, everyone said, oh, yes, that's how enzymes work. Okay. So it was a driving force. And I got my PhD in 1966. So you can see that was a long time ago. But that was the explanation that people gave. And that's just a definition of catalysis. It doesn't really tell us how enzymes work. So the field has changed dramatically since then, because really what we want to know are the physical properties of an enzyme that allow it to accelerate rate reactions by maybe 10 to 30 orders of magnitude relative. That's huge. They catalyze rates at huge rates, rate accelerations, and it can't just be this transition state stabilization. But it's taken many years for people to let go of something that a famous chemist like Linus Pauling proposed. People still report that sort of understanding in the literature, but our ability to explain enzyme catalysis has moved way beyond that. But that's where it was when I started out. If it's not clear, if anything's not clear, just ask me and I can explain more.
So, Professor, you may be having great experiences in your life. What are the most unforgettable memories that you had?
Before we got together, I actually sat down and made some notes. I'm going to read from that because I thought that was a great question. So I want to congratulate you on that question. I like it a lot. And it wasn't deciding to become a chemist or anything like that, which was a great thing. But so when I was quite young, in my 20s, I had my children. I have 2 boys, and we have had 8 grandchildren by now. But starting a family, I mean, that was big. That was huge for me to start a family, and figuring out how to raise a family and how to have a career in science. That was a real challenge. And so that was a great experience. It was not always easy, but it was a great experience. We lived in Israel, so I'm Jewish, and we moved to Israel to a place called the Weizmann Institute of Science, which is in Rehovot, which is near Tel Aviv, which was a research institute, and we were there for almost 2 years. So moving to another country, the Middle East, and getting to see how other people live it, that was a great experience. The next one was moving to California in 1978. So I was working in Philadelphia. You can read, by the way, I sent you a chapter that I didn't give you enough time to read it, but you're welcome to read it and you can fill in the blanks. But anyway, I moved to California as the first woman in all the physical sciences at UC Berkeley. That was terrifying for me, and also it was a great experience because the whole world opened up to me when I did that. It became a whole new life for me. And my kids were adolescents. I was getting divorced from my first husband, and a great husband, but we just couldn't make it last. And later met the man who is my husband now, and we later joined forces. We each have 2 children to make a family of 4 children. So that worked out well. But the main thing was, my God, California was like moving to another country at that time. And it was wonderful. I loved every minute of it in those early days, and I still do. And it makes me very sad that we have all these fires and crises right now, but it was a great experience. I have had some wonderful personal experiences. I did I guess it was a 1-month trek in Nepal, up into the Himalayas, up to 18,000 feet. I did it, I succeeded. That was a great experience. I went on a safari in Africa to Botswana and got about this close to the big lions. And, it was like, that was a great experience. I met Barack Obama. That was a great experience. And, seeing our family grow, and, we're kind of old. I'm close to turning 80, and just seeing this large family, that it includes an academic family, not just a biological family. It's just all these people that come into your life and form a part of your life. So I think I've had lots of great experiences. It's a great question. Thank you.
So you were able to break down some of classical methods. How would you overcome these challenges?
Yeah, so really, I was trained as a physical organic chemist. And physical organic chemists want to understand how things work. And one of the tools for understanding how things work is to incorporate isotopic variants of the elements into your molecules that you're studying. So I learned how to do kinetic isotope effects as a graduate student. And as I was going along in my career, I applied them. I did many things in chemistry, biochemistry, biophysics, but in the early days, I was measuring isotope effects, and we started to see things that didn't agree with what was predicted. And, I'd been trained by some of the masters, and it was very hard for me to turn away from the classical point of view. But eventually it became impossible to accept it. And this is how we came up with the whole idea of hydrogen tunneling, because within transition state theory, there are all these predictions. And as we went along more and more, what we were seeing could not conform to transition state theory for hydrogen transfer. And it was in the context of these isotope effects that the measurements didn't match up with the predictions. So I think in terms of the actual methods that we've used, that's a tool, isotope effects. I mean, we use every tool we can get our hands on, right? Whether it's spectroscopic or structural or kinetic. So I don't think it's the method, although we have developed a new tool in recent years, which involves something called hydrogen deuterium exchange, which the temperature dependence of it. But I don't think our strength is in method development. I think our strength is in collecting data, sitting back and recognizing when it doesn't conform to the expectation.
Your research field is most related to the biological field and also the improvement of medical field. Were there any changes that happened in medical field since your findings?
Well, hydrogen tunneling is, there are lots of applications. It's a field called quantum biology now. Everyone knew that the electrons move as a wave, but now that we know that the hydrogen does, there are all kinds of potentials down the road. But I think the actual change that's probably the most important is that when people design drugs, number one, they were trying to design drugs that look like the transition state, because that was the whole theory, that the enzyme would be complementary to the transition state. Well, it didn't work very well. And people then had to use screening instead of design based on mechanism or whatever. So clearly something was wrong. And now what's happening is that the role of protein dynamics, which is very much related to the ability of a particle to move as a wave, and that's really what the tunneling is all about. The particle is moving through the barrier, not over the top of the barrier. It's moving as a wave. And motions in the protein are very important for setting that up. And what has happened in drug design now is people are they're not taking static structures of proteins as their context. They're letting the protein move. And it's through these dynamics that they're now optimizing the effective binding of the drug to the protein. So it's incorporating these dynamical aspects. And I think most people are certainly using that as a paradigm for how to go forward. Actually, a lot of drugs are still found. So drugs largely target enzymes, and a lot of drugs are still found by screening. But I do think that this use of dynamics is making a difference. We'll see.
So, what are the upcoming research investigations of your field?
Oh, yeah, for sure. So what we want to do, there is no question in my mind about that one. And this also applies to the future. It's not working. We want to do de novo design of protein catalysts that work as well as the natural occurring evolved catalysts using the principles that have come out of our studies. So I don't know, I'm sure you know Frances Arnold got a Nobel Prize for protein evolution by saying, well, we can't design a protein from first principles, so we're going to let the bacterium evolve the enzyme according to its growth conditions and get a better enzyme. I mean, that works to some extent, but to us it's very unsatisfactory because what we want to do is understand how they work so well that we can use those principles, and then it has enormous applicability. I mean, we could design catalysts for many different things, de novo. And I think we're getting closer to being able to do that. I really do believe that. I mean, we could go into the details, but that's not the purpose of this interview. I think that it's a very dynamical, it's a very fluid field right now, and more people are looking in new ways at understanding catalysis, and then the goal, of course, is to show that we can do this de novo design. And well, we'll see. But that I think is a goal of most people who study catalysis, really, because proteins are the most powerful catalysts that we know. And if we could capture the essence of their catalysis, I mean, just the possibilities with green chemistry, for sure, everyone talks about that. But then the possibility of, designer enzymes. People have tried computationally, so we can't do it computationally. We really need these underlying principles. And by the way, the computational chemists, they were not incorporating these dynamics of the proteins. You'll see, I'll sound like a broken record because I really think this is key to what's going on. Yeah.
You have already told about nuclear tunneling.
The first thing is tunneling is a fundamental property of nature, right? Particles are waves. They don't always display their wave property. They look like they're fixed in space. They have mass, but particles have waves. You have a wave. You have a wave function. It's just very short, very small. The smaller the particle, the larger the wave function. The larger the particle, the smaller the wave function. Hydrogen's kind of in between. But everyone had known that a particle can behave as a wave and pass through a barrier. It doesn't have to go over the top. But that was always at low temperature, right? So if you go to low temperature, you have no heat to put into the system, and the particle behaves as a wave. If you wait long enough, you can see it move through the barrier instead of having to go over the top. There's no energy to bring it over the top. So every now and then it will go through the barrier. But enzymes do that at room temperature, not at absolute zero, 4 Kelvin. So that's really the crux of what's going on here. And so that means that something else has to be facilitating tunneling at room temperature, right? The particle itself won't do it unless it's facilitated somehow. And that's what proteins are doing. But what's so interesting about this is one of the major dilemmas that came up in quantum physics when it first emerged was, how do you reconcile the macroscopic behavior of nature? Nature is largely macroscopic, right? And as I said, you're macroscopic, I'm macroscopic, the chair is macroscopic. How do we reconcile the macroscopic properties of nature with the microscopic quantum behavior? And that's what enzymes have figured out how to do at room temperature. The secret lies in the coevolution of the protein scaffold, the macroscopic protein scaffold, which can then promote this very microscopic quantum behavior in the active site. So I think that's part of the interest also in terms of just physics rather than biology or molecular biochemistry, molecular biology. I think that there are, once again, rules there that we can draw on for making new devices, for example, if we want to create quantum properties within a device, and how do we then create the quantum behavior or sustain it? How do you sustain quantum behavior? Anyway, there is something there that I wouldn't have expected, but that's what turned up. So I think the tunneling has turned out to be far more interesting than just, oh yes, it can be a wave and it can move through the barrier.
Recently, you have awarded Penn Chemistry Distinguished Alumni Awards. Could you please tell us what drives you to achieve such excellence in the field of science?
Oh, wow. Huh. What drives me to do it, huh? You know, honestly, I never expected to be a professor, ever. So the last thing in my mind, I think it's curiosity. You know, really wanting to understand how the world works. That's what got me going. Of course, everything else, it takes on a different flavor when you're engaged, and then you have colleagues and challenges. And, you know, we haven't just studied tunneling, we've studied a lot of other things in biochemistry and, you know, mechanism, and discovered some new cofactors and, you know, all kinds of stuff like that. So there's that, the hunt. It's the hunt to understand. You know, you actually go on a hunt. Something, you either ask a question that hasn't been asked before, or something shows up that doesn't make sense, and then you know, all right, I'm on the trail, and can I understand this, and can I really bring it, make it into a fruitful kind of discourse and subject matter. So I guess what drives me is trying to get to the bottom of things. You know, I want to know how it works. And there is a spiritual component to that as well. My son, who is not a scientist, but my older son, but, you know, always prods me. What are you doing? Why are you doing it? And when I talk about some of this stuff, he says, well, isn't that what spirituality is about? Trying to understand the nature of reality. And so there really is this close link between hardcore science and spirituality. I don't know, I don't want to sound too woo-woo with you, but, you know, I do think that it's just the quest to understand how things work and what is the true nature of our reality. So that's been driving me, and I was always curious as a kid. So, but I want to say something about the Penn Award, because since I got my PhD and undergraduate degree at University of Pennsylvania, it meant a lot to me. And just being called back to be honored by my department was a very big deal in my life. And my PhD advisor, who is retired, came. And so I want to say that each of us should have the chance to be honored by our alma mater at some point in our lives, if we're lucky. And I did also get an honorary PhD from U Penn earlier than this award. So I feel very touched by that. I feel very honored by my alma mater. Yeah, maybe what happened for you at Colombo University.
You have gathered experiences through several decades in your life. So my last question is, what is your advice to next generation for being passionate about science?
Oh, wow. Well, I think you are passionate about science, I would assume. You're here interviewing me, and also you're graduating. You're going to go on for a PhD, if I understand correctly. So what does it mean to be passionate about something? I think for me, you know, I found something that I loved and that I'm also good at. And so you get this positive feedback. You you move in a direction, your interest goes somewhere, and then you get positive feedback, and so you keep on going in that direction. I feel incredibly fortunate that that has happened in my life. I've also been lucky, of course, in being in a great place to be able to do science. So, but there were many junctures at which I wasn't sure I could do it. You know, I've put on a brave face most of the time, but there have certainly been times when it's been hard. You know, every time we came up with a new idea, there was a lot of pushback, and my poor husband had to listen to me moan and groan over, oh my God, why don't people come on board, and why don't they see clearly what we see? So having a good person at your side who's your friend and who really encourages you has helped me sustain my passion. You know, I'm living with a man who really believes in living a passionate life, and an intellectually and emotionally passionate life, which allows you to really live fully. So I've been supported in that way. He's not a scientist, and so sometimes I wish we could talk science together, but we do understand, we do share that understanding and passion. You know, as a woman, be strong and don't let yourself get derailed by people. Listen to yourself more than anything. Have the confidence to follow whatever interest arises as you're doing your work, and you know, stand fast. Be sure of yourself in that way as much as you can, because women have a unique view. So I'm addressing you as a young woman in science too. Women bring a unique view to science, and I remember being told by my first two my second graduate student, who is now risen to a professor of distinction at University of Colorado Boulder. Her name is Natalie Ahn. And I remember saying to her, we would talk about the science, and I would push back at her, and I would say to her, what does your intuition tell you? And she would become furious with me. Oh, science isn't about intuition. Of course, that's not true. There's a huge amount of intuition that comes along with all the intellectual activity and what you learn, the hardcore science. So I think also learning to trust your intuition in terms of things. Yeah, don't let people, I did write something down on this one. Don't let people tell you what they want you to do, but do what you want to do as much as you can.
I think you were the first female professor.
At the University of California, Berkeley, I was the first woman professor in all of the physical sciences, yes. So
Now we have moved to the end of today's session. So is there anything else you would prefer to add?
no, I think if I have, as I said, written this chapter a couple years ago, and you may want to take a look at that, because I did spend a fair amount of time trying to get it right anyway for the time, and think about what was important to me. So I think you've asked terrific questions. By the way, one of the great things about being a scientist, on top of everything else, is all the people you get to meet, the people you interact with, the people you train, you know, the travels, although hopefully travels will be more restricted because of climate change. That's another issue that's become very, very important in my life. But it's a community. You join a community, and it's a very rich community of people from your own country and from around the world.
So it's a pleasure to interview you, and thank you so much, Professor Judith, for joining today and share your knowledge, great experiences with us.
You're very welcome, and good luck to you. And do I get to see this? Or maybe I don't think I want to. No, of course. But the best of luck to you as you go forward. And let me know. Keep in touch. Would you? Just let me know.
Thank you.
You're very welcome.
Today we have interviewed Professor Judith Klinman from Department of Molecular Biology and Cell Biology, University of California, Berkeley. Hope you all had really enjoyed this session with a distinguished professor in America. Have a nice day.